Hello, and thank you for coming to Sig School Scholars. Today, we're going to be talking about Newton's Law of Universal Gravitation, and Newton's Law of Universal Gravitation, how it relates to circular motion. So, let's dig right in. Newton's Law of Universal Gravitation, they said all particles in the universe attract every other particle in the universe with a force that is inversely proportional to the distance between them. Well, the square of the distance. Well, whoops, that's not good. Force that's inversely proportional to the square of the distance between them. Oh yes, and the direction of this force is along a line separating the two masses. So this is mass 1 and this is mass 2. Force that they exert on each other. And of course, because Newton's third law of motion, we know that the force that mass 1 exerts on mass 2 equals the force that mass 2 exerts on mass 1. So, force on 1 due to 2 equals force on 2 due to 1 in magnitude. Direction, the directions are opposite, of course. So, the magnitude, the direction is again along the line separating them. The magnitude of the force is equal to G m1 m2 over r squared, where G is the gravitational constant, which is approximately 6.67 times 10 to the negative 11th newtons times square meters per square kilograms. And as you can see, the newtons the units are this in order to cancel out everything besides newtons, which is what the force is measured in. So, square meters cancel out with the denominator, square kilograms cancel out the numerator. What we have left is newtons. So, let's say we have, so the force of gravity is not a very strong force compared to other fundamental forces, which we're not going to talk about right now. So let's say we have two masses where mass 1 and mass 2 are both, 2,500 kilograms. They're both hung from strings. And we're trying to see if they move towards each other. And this is, I guess string is not the appropriate word. Maybe cables. Yes, two masses, dots, because we are in physics class, I guess you could say. Technically in physics class. So, we have a force acting on line of separation. We'll say that they are 1 meter apart. This will demonstrate the weakness of how weak gravity really is. So, the force that m1 exerts on m2 and m2 exerts on m1 will equal G times m1 m2 over r squared, which will be, if we put into the calculator, 6.67 times 10 to the negative 11th times 2,500 times 2,500 divided by 1. Our answer is a whopping 4.2 times 10 to the negative 4th newtons. And then that's along that line of separation. That force is minuscule and will lead to a acceleration of 1.67, well, 1.7 times 10 to the negative 7th meter per second squared. So it's not really measurable. It's insignificant. When it becomes significant when we were talking about objects of astronomical masses, literally. When we were talking about objects with masses that are masses of planets and stars. So let's say, okay, we have this formula. If we have a okay, yeah, we measure the force at R equals 1.00 meters. We get a force. We measure it at, let's say, at 0.5 meters. Or how about we say we measure it at R and then 1/2 R. So R1 and 1/2 R1. So we'll say that the force is obviously going to change because R changes. But let's find out how much it changes. So we know the force, let's just R1, distance R1, will equal some constant multiple of when it's at R2, which is 1/2 R1. Let's find that constant multiple. So it's going to be, well, we can cancel out all these. We get 1 over R1 squared is equal to K times 1/4 R1 squared. 1 over R1 squared. So we multiply both sides by that 1/4 R1 squared. So we get R1 squared wait. Yeah, let me make this a little bit neater. K over 1 over 4 R1 squared. Write that as 4K divided by R1 squared. So 1 over R1 squared is equal to 4K divided by R1 squared. So, well, there is our answer. 4K equals 1, of course. Because if our denominators are equal, our numerators must be equal. If these are equal to each other here, this is equal to that, and our denominators are equal, then our numerators must be equal as well. 4K equals 1, which means K equals 1/4. So, that means that if at radius 1 we had a force of Fg, then at radius 1/2 R1, which is, we'll say, R2, we'll have a force of Fg over 4. So, okay, wait. That is that's not really, wait. No, what I meant, okay, here, that K is equal to 1/4, right? So, if K equals 1/4, that means that at this first radius, we have a force at FG1, and then that FG1 is 1/4 of our FG2 at this new radius, which means that FG2 is 4 times as great as FG1. So when we half the radius, the force multiplied by 4. And we'll see the same rule if we triple the radius. Divide the radius by 3, force will increase by 1/9. By 9 times. 9 times great. However, if we multiply the radius by 2, the force will decrease by 1/4 what it was. It'll become 1/4 what it was. If we multiply the radius by 3, the force will become 1/9 of what it was. So the force function of radius will look something like this. It decreases exponentially. And as r approaches infinity, force will approach 0. Which you can see, because if we multiply the r by a really, really large number, the force would greatly, greatly decrease. Proportional to the square of that change. Okay, so now that we understand that, let's do a single problem. Let's do a problem with that. So the problem says that it asks for the force of gravity on a satellite of mass 2,000 kilograms, or spacecraft, or whatever, doesn't matter. That's orbiting the Earth at 3 Earth radii. Okay. Now, well, based upon what we said, first, remember, this is the force acting between two objects of at a distance of r, and with masses m1 and m2. Well, the weight of an object on Earth's surface is the force of gravity acting on that object, m2. So m2 times g will equal this force. They are the same. So, remember we said that if we were to triple the radius, then the gravity Fg, let's say nu, will be times 9 is equal to Fg old. And we already saw how that would work, which means that the weight of that object in space, or the force of gravity acting on it, is going to only be mg divided by 9. One-ninth of its original. So 2,000 times 9.80 divided by 9. So force of gravity acting on it is 2,180 newtons, as opposed to the force of gravity. The force of gravity acting on it, if it were on the Earth's surface, however, would be 19,600 newtons. So there you go. Okay, here, let's clear this. So now, let's explore this relationship a little bit more. So, in the case of the Earth, if we're talking about the Earth, well, M2 is just some object, some distance r away from the Earth's surface. From the Earth's center, I mean. And, so this is the distance from the Earth's center. Okay, so this is for the Earth's center. If we're talking about the Earth, M2 is just some object. So on the Earth's surface, basically what we have is that GM1 mass of the Earth M2 by the radius of the Earth squared. So these M2s cancel out, and then the gravitational constant times mass of the Earth divided by the radius of the Earth squared will equal G, gravitational acceleration. Now we can extend this to apply to any planet, star, surface of the surface gravity of any planet, star, whatever, by just saying the G times the mass. Let's just make it big M, because it's going to be a large mass, over R squared. So, for example, if we had the mass of the moon and the radius of the moon, then we could find the gravitational acceleration at the surface of the moon. Also, we could go back to the case of the Earth and find the gravitational acceleration maybe at some different radius. But instead of putting in RE squared, we put in RE plus wherever we're talking about. Maybe Mount Everest. We decided to do Mount Everest, which is what, 8,000 feet elevation, 8,000 meters, I mean. We put that in and we square it instead of RE. And that is gravitational acceleration on top of Mount Everest, for example. So we can find the gravitational acceleration on any planet, star, anywhere, by multiplying the gravitational constant by its mass and dividing by its radius squared. And we can do the same thing on the surface of the Earth, and this would give us the gravitational constant if we just used the radius of the Earth. If we maybe added in something like at the top of a volcano or a mountain, or in a deep sea ridge or whatever, we would add or subtract that from the Earth's radius, and we can do the same thing with this formula. So there's that. And yes, the gravitational acceleration differs at different points on the Earth. So like on top of Mount Everest, for example, we have well, not really much lower, slightly lower gravitational acceleration, off by a few hundredths of a meter per second squared. So now we're going to go back to circular motion. And what we're going to look at here is circular motion, but in space, like orbital motion. Well, let's say we have two objects in space. Or one revolves around the other. Some velocity. You may ask, what provides centripetal force? Centripetal force is provided by gravity. And that's what keeps the planet moving around the object. Maybe the Earth around the sun, the moon around the Earth. So we know that that force of gravity will equal G m1 m2 over r squared. This is, of course, m1, this is m2, and this is r, the distance between them. So we also know that for an object traveling around a circular path, the force required to keep it traveling in that path is equal to mv squared over r. So with that relationship, well, we know that these two must be equal. And what we can do is derive some formulas to find the velocity, maybe, that an object must have revolving around another object at a certain distance. Well, we can go ahead and derive that formula. Velocity, square root of g m, let's say the Earth, over r e. So we're talking about here. In this equation, this is the velocity an object of well, here, plus height, whatever height it's at. Okay, this is the velocity a object must have if it is to travel around the Earth in a circular path, if it is traveling at a distance from the Earth's center of the Earth's radius plus whatever height it is from the Earth's surface. So, for example, if we were talking about the speed of a satellite orbiting 200 kilometers of Earth's surface, we would take the square root of g me over the Earth's radius was 6.38 times 10 to the 6 meters plus 200,000 meters. And put in gravitational constant. And the mass of the Earth. We put those in. Okay, divided by the result is around 7,780 meters per second. That's what we get. That is velocity, for example, of a satellite, 200,000 kilometers. Whoa, that'd be really far. 200 kilometers or 200,000 meters from the Earth's surface. Okay. So, and as you can see, the result is independent of the mass of the object. Only on the mass of the object it's revolving around and the distance. Of course, different formulas can be derived for the radius, for the period, and for other concepts or characteristics of an orbit. And it works the same way as circular motion, where we have a radial force that's causing the circular motion to happen. That radial force in this case is gravity, and that is how it works. So let's do a few problems. with this. We probably don't need to do problems with the universal law of gravitation, because it is simply putting numbers into an equation. But this particular problem will be interesting. Let's see. We know that two objects attract each other with a force equal to 2.5 times 10 to the negative 10th newtons when the distance between them is 0.25 meters, and their total mass is 4.0 kilograms. So we need to find their individual masses. Now, how are we going to do this? Well, we're going to need the law of universal gravitation for this one. So what we know is we know Fg, we know R. We don't know M1 and M2. So what we're going to have to do is write, let's say M2 in terms of M1. In order to do that, we'll say M2 is equal to 4 minus M1. And then that way we get a quadratic equation. So Fg will equal G, big G, times M1 times 4 minus M1 divided by R squared. And this, we only have one variable. G will equal G times negative M1 squared plus 4M1 divided by R squared. And we'll multiply this force, 2.5 times 10 to the negative 10th, times the radius squared is 0.25, is 0.625, and divide by the gravitational constant, 6.67 times 10 to the negative 11th. We get 0.234. So 4m1 minus m1 squared is equal to 0.234. 257871064. So quadratic equation, use quadratic formula, solve it. Negative b plus or minus square root of b squared minus 4, no, will be minus, so we have minus negative 4, negative c, negative 0.234, minus 4 times 0.234, and we have 0.937, which isn't very much, and not gonna be much difference. Oh yeah, divide by 2 times a, which is negative 2. So m1 will equal, put that in, negative 4 plus the square root of 16 minus that, divided by negative 2. So we get a mass of 0.06 or so. We have 0.059, really. Okay, and let's see what the other solution gives us. I would imagine it would give us the other the other value, like what M2 would equal if M1 is at 0.059. Let's see. It should give us that. If it doesn't, we can just, well, we'll see what happens. Huh, well it does. 3.941 about kilograms. When we add those together, we'll find that they equal 4 kilograms. So we'll just name that one M2. So these are the masses. Let's look at a couple more problems. A couple more interesting ones. This one is particularly interesting. So, it says that a typical white dwarf, okay, once was an average star like our sun, now the last, okay, size of our moon, so there's a radius of the moon, and mass of sun. Wow. This is going to be interesting. What's the surface gravity? So, remember, gravity, the weight of an object is force of gravity acting on it, and it's going to equal okay, so it's going to be the weight of an object is going to be, you know, the force of gravity acting on it. Remember, we cross these out. We get G equals GM1 over R squared. So, we can do this a couple ways. We can write the mass of the moon in terms of the mass of the sun, the radius of the sun. Compare them and use the constant term we get to show how many times this gravity will be than that on the sun. But that would be much harder than this method, in which we simply put these in. So the mass of the sun, 1.99 times 10 to the 30th. Okay, wait. We're going to divide by the radius of the moon, which is 1.74 times 10 to the 6th meters. And what we get, wow, well, it is 7.63 times 10 to the 13th meters per second squared, which is awesome. That is 7.78 times 10 to the 12th G's, or 7.78 times 10 to the 12th times greater than gravitational acceleration of the Earth. So you would not be able to live on that. You would certainly be crushed by the gravitational forces. Oh wait, I think I made a small mistake. Wait. Yes, the mistake I made was that I only divided by r and not by r squared. When you divide by r squared, you get slightly less ridiculous answer, but an answer that is still incredible nonetheless. 4.38 times 10 to the 7th meters per second squared, which is 4.47 times 10 to the 6th G's, which means that a 50 kilogram person would weigh in at about 2.24 times 10 to the 8th kilograms. I mean, newtons. 50 kilogram person would weigh about that much, which is a lot. White dwarf WD. Okay. So, couple more problems. Let's say we have okay, a hypothetical planet has a radius 1.5 times Earth and the same mass. So, well, we know that since the size of the planet increase, the distance from the center of an object will be on the surface will be larger. So it's going to be smaller. The gravitational acceleration is going to be smaller than it is on Earth. GMB divided by, and we'll put in 1.5 times Earth radius squared. And that will give us an answer that, once we square it, should be correct. .36 meters per second squared. Okay, so that is circular motion and gravitation. Thank you for watching the video. If you want us to make a video on a specific topic, just leave a comment either in the comment section below, or on our website at sigschooltours.wordpress.com. Try to fulfill your request as soon as possible. Thanks.